So if your integrand has a branch cut, this actually can help a lot with getting the integral. So a typical contour. So the thing about branch cuts you have to remember is that because there's a discontinuity at a branch cut, you're not allowed to integrate through a branch cut. But that's not a problem, because what you can do is integrate around a branch cut. This is what a typical integral of a function with a branch cut looks like. You've got a big circle, but as soon as you get close to the branch cut, you're not allowed to integrate through it. You integrate along it up to the and around the branch point and then back. Now the key thing about branch cut, remember, is that the value of the integral, the value either of the function either side of the branch cut has a discontinuity. It's not the same value either side. So that means that this integral along here will not cancel this integral along here, and that's useful. Now, very often what happens is this integral along here is the integral you want to find, and this integral along here is a multiple of the integral you want to find, and a multiple which is not -1 times the integral you want to find. Otherwise the two would cancel out and it wouldn't be a branch cut. Yes, just one note. So don't confuse branch points with singularities. They're definitely not the same thing. A function can easily be finite at a branch point. So for example, square root of z has a branch point at 0. Obviously it's finite at z equals 0. Yes, as I've said here, if a function is finite at a branch point, one thing you do have to be careful about is that we actually need to integrate around the branch point. If you ever look at other books, you tend to see a circular integral around, a circular loop around the branch point. I just use a semicircle, and that works. That generally works okay. There's no particular need to do a whole circle. It just makes things more complicated. If there's any instances where you do need to use a whole circle, then I'll say. But semicircle is fine. If you've got a branch cut along the real axis only, these are two typical contours that people use. When we come to it, I'll explain which one is easier to use in which cases. Just save some work. I mean, basically, if you can, you probably want to use this one. If it ends up giving you the integral you want, basically because you'll have half, and generally you'll have half the number of residues to evaluate. Obviously, if you integrate this, then it's saying you have to evaluate all of the residues of the function, all its singularities. Here, you only need to look at the singularities above the real axis. So obviously, if you can, you try to use the one in part B if it's possible. Okay, so let's see how all this works with this example. So we want to find this integral here, the integral from 0 to infinity, and this power a is some number between 0 and 1. So we're doing this, yes, very much in detail. In this particular case, unless you know otherwise, you should use this contour. If you have a good reason to suspect that you can get away with this contour, then okay, you'll know and you'll use it. But okay, to start with, we're going to use this contour. Okay, so we use this contour and take the limit as r goes to infinity, and we're going to say this radius of the semicircle epsilon, which is basically the distance between the contour and the x-axis, epsilon, goes to 0. So we now have two limits. So it's the limit as r goes to infinity and as epsilon goes to 0. So the integral we want is this line integral here, as r goes to infinity and as epsilon goes to 0. So that's I. Then we have the integral around this circle, which is from theta equals 0 to 2 pi. Well, okay, as usual, z equals r times e to the I theta. Differentiate with this respect to theta, the I comes down, you end up with this. So this is dz. Then you've got, well, we're considering z to the a, z plus 1, so that this is where the z is z plus 1, and this is z to the a here. Right, now this is the important bit. When we come back along here, so we're round to here, we come back along here, this is the essential bit. So whatever happens, you know that because there's a branch cut here, this integral here should not be the same as this integral here. If it is, then you've done something wrong. So the trick, well, it's not really a trick, this is what you need to do. Along here, you need to write z as not equal to x. Along here, z was equal to x, no problem. But remember, theta, with a branch cut here, theta varies from 0 up to 2 pi. So along here, effectively, theta is 2 pi. So you need to write z as x times e to the 2 pi I. Now, obviously, if you're not raising that to a power, then x times e to the 2 pi I is the same as x. So that's fine to leave it like x here, where you're changing the z plus 1 to x plus 1. But you see here, you do need the e to the 2 pi I, because you're about to raise it to the power a, and that's going to make a difference. That's basically why you've got the branch cut here for this function z to the power a, where a is not an integer. Okay, so that takes us to here, and then finally we have this little bit here. We need to check that that goes to 0. So again, it's the same integral as this, but we have epsilon instead of r, and we're taking the limit as epsilon goes to 0. Okay, so we need to check that both of these integrals go to 0. So firstly, this one, we just look at the r, and this is all modulus 1. We've got r divided by r as r goes to infinity, so this cancels out, and then we've got r to the power a is larger than 0, so this will tend to 0 as order r to the minus a. Then this integral here, remember we're looking as epsilon goes to 0 this time, so this is going to be 1, we don't have to worry about that. We've got epsilon divided by epsilon to the a, so it's basically be epsilon to the power 1 minus a, and as long as a is not more than 1, then this will go to 0 as epsilon goes to 0. So we're fine, these both go to 0, and we're left with the integral we want and this integral here. What we're hoping is that this integral here will be a multiple of the integral we want. And it is, indeed it is, because okay, we can obviously take out a factor of e to the 2 pi I a, and then that's just this, we're left with this integral here. So we have to be careful to get the signs right. We put a minus sign and swap the limits, and we've got an e to the minus 2 pi I a outside. So we end up with this thing is equal to the 2 pi I times the sum of the residues of this. Obviously this only has one residue, I mean one pole, one singularity, which is that z equals -1. So the residue there is using the p over q dash method. Q is the z plus 1, so it's just q dashed is 1. We've just got 1 over, again we have to be careful evaluating the residue a little bit. So it's at z equals -1, we have to write z equals e to the I pi. Okay, it can't be e to the I minus pi, it has to be e to the I pi, because theta is between 0 and 2 pi. So z equals e to the I pi, evaluated at 1 over za gives you e to the minus I a pi. So that's our residue, and rearranging and simplifying gives us the answer. Okay, so if f is even, the function we're integrating is even, and we've got some b, so yes, I've given some formula. Well, whatever you do, don't memorize this formula. Okay, I think I'll save that for the next video.